Hey, so those are the same as last week. So you have your from last week, you will need a new one. If you need a new one, we have those around. We'll start with something else, whether it's not, have those around. All right. Okay. Hi. Hello. So the plan today is to introduce project 2. So project 2 is not due until after the midterm. That means that it is not technically on the midterm, I suppose. With that said, I think it's still good practice, but when so you should do project 2. It's as good in terms of practice for the midterm as any other exercise. At the same time, it's not the kind of thing where I would say, well, I expect them to have done that kind of problem, so therefore I would put a similar problem on the midterm just to see if they had done project 2, because that would be not fair to do on the midterm. On the exam, on the other hand, it would be extremely fair to do. So that's kind of the situation. So I'll just introduce what project 2 is. So what you're doing there is you're building a game engine for a game called sometimes Gomoku, sometimes 5 in a row. So I think like most people are like not from how many people have played this game? And so I actually many. Okay, that's good. So for people who don't who never played the game, it kind of looks like this. You can think about it as tic-tac-toe, but on a larger board, and you need to get 5 in a row rather than 3 in a row. People usually play those on Go boards, and they place the black and white stones at the intersections, just because it's kind of annoying to render Go boards, or like not that annoying, but they didn't do it. I placed the black stones and the white stones in the squares rather than the intersections. Of course, the principle is the same. Okay, so so here those are kind of impossible positions, right? So because you place the black, then you place the white, then you place the black, and so on in turn. So that's not the kind of thing that would happen, but the gameplay would be, black goes, white goes, black goes, white goes, until one of them has 5 in a row. So the handout walks you through one strategy of making the computer play. I made it so that it actually plays pretty well. So if you don't pay attention, it can probably win. I saw that some people lose to their tic-tac-toe engine, but you know, it's pretty good. So I want to introduce. So I'll do the midterm after that. So I want to introduce kind of the idea of how artificial intelligence in board games works in general. This is more kind of a general story rather than something that's directly applicable to Project 2 or the exam, just like to give you context, but there will be a pretty direct connection as well. So this, by the way, is linked from, I'm now making a week by week kind of thing. The slide deck is linked from the last slide in our big slide deck. I'll do like week by week from now on. It's grown too large. So, okay. So the history, I think people generally know. So in 1996, Deep Blue, lost to Garry Kasparov in chess. So that's like maybe not remarkable, but it played well enough that, you know, like the next year it improved and it beat Garry Kasparov, at the time the world champion in chess in 97. So in 2016, not that long ago and not that much later, AlphaGo beat Lee Sedol in the game of Go. So Lee Sedol, not literally the world champion, but one of the best Go players in the world. So things have been improving. So how does it work? So in general, you can decompose a program that plays a board game using artificial intelligence into two components. This is slightly simplified, but that's okay. So you have what we call an evaluation function. So an evaluation function takes in a position. So, you know, a chessboard with like which pieces are where, or a tic-tac-toe board with which pieces are where, and so on. And then it outputs a score. And a higher score means player one is doing better. A lower score means player one is doing worse. Okay, so in chess, we'll see in the next slide, if you were taught chess, you were probably taught something like an evaluation function. So you were probably taught that a bishop is like 3 pawns, right? And a knight is like maybe 2.5, according to some people, stuff like that, right? So measuring how well you're doing in terms of how many pawns you have, that's an evaluation function, a quite primitive one, but still. So we'll have more examples if you haven't done chess in a second. The other component is search. So it's not enough to know that if I get to this board state, then I'm winning. You also need to know how to get there, whether you can get there. So search refers to trying to think of different moves and say, you know, if I move that way, my opponent can move that way, and then I can move that way, and so on. It's not possible to exhaustively look through all the possibilities in any game that's like not tic-tac-toe, because there's just too many possibilities. So search refers to clever workarounds of around not being able to actually exhaustively look through all the possibilities. So this is kind of a famous XKCD cartoon, which makes the point that in tic-tac-toe, it's totally possible to look through all the possibilities, and there is, you know, a strategy for doing this. So this is the visualization of the strategy, right? So the idea here is your move is whatever's in red. So if you're X, then you should go here, and then you can look up where your opponent goes, and based on that, there is an optimal move in tic-tac-toe. The reason we know is that you can think exhaustively through which moves in tic-tac-toe lead to you at least not losing. So there is a strategy. So, okay. So let's talk about kind of concrete examples. So in chess, like I said, what they teach you is, how do you know how well you're doing? Well, look at your pieces. You could look at your opponent's pieces, count up the worth of each piece in pawns, or sometimes people use like centipawns, so like 1/100th of a pawn or something like that, and compute your score. You can do much better than this. Deep Blue did much better than this. So they had a handcrafted evaluation function that looked at much more than this. For one, you might imagine that, famously, if you are about to be mated, it doesn't matter how many pieces you have, right? So you might like to look if your opponent can win in one move. That would override whatever material advantages you have. So this is just talking about chess for a second. You can think about kind of squares on the board, and you can count how many threats there are on this square. If you know chess, you maybe know what I'm talking about. So that also goes into the evaluation function in terms of how many squares you control, stuff like that. How many people played Go ever or know the rules? Okay, so I'm terrible at Go, but even I know that the strategy with chess works much worse than Go. So you can count up how many stones you have and how many stones your opponent has, and that tells you nothing. You can even count up, the amount of territory that you currently have and the amount of territory that your opponent currently has, and that tells you something, but not very much. You can count up the number of eyes, whatever, right? So like there is ways, but it doesn't work as well. So that is probably, in my opinion, this is not kind of set in stone in terms of completely understanding why, but that is probably why making a computer program to play Go well was harder and historically happened later than a computer program that plays chess. It's just difficult to explicitly say what is a good Go position and what is a bad Go position. Professional Go players famously kind of just glance on the board and get the sense of I'm doing well or I'm about to lose, although they, of course, also calculate. So that's chess and Go. So if you haven't played chess and Go, this might sound a little bit opaque. So what about tic-tac-toe? So that is what we had done in the lab last week. So what would be a good evaluation function for tic-tac-toe? How do you know that you're doing well versus you're not doing well? Anyone? So like if you see, a tic-tac-toe board, you can probably tell whether one person is doing well or not. How do you know? Anyone? Okay. Yeah. Yeah. So if their next move could lead to 3 in a row, that is doing well, right? Except if the opponent is about to win, then it doesn't matter, right? So we can kind of formalize it. So we can say count up the number of ways you and the opponent can complete a sequence of 3 in one move. Right? So that's pretty good. So if I can complete a sequence of 3 in 2 ways and my opponent can just do it in 1 way, I block my opponent, and then there is nothing they can do, and then I win. Right? So that would be an example of an evaluation function. So just how many ways can I complete a sequence of 3? And if it's 2 ways, then I'm doing better than if it's just 1 way, because if it's 1 way, my opponent is just going to block me. Does that make sense? Questions, or do people want it to be more explicit, or is it good? Who wants it more explicit? Okay. All right. We'll do a tutorial on playing tic-tac-toe for anyone who's trying. So okay. Anyway. So that's an example of an evaluation function in tic-tac-toe. So modern evaluation functions are not like that. So AlphaGo, the system that beat Lisa Doe, is not like that. So it doesn't have explicit rules about what makes a good Go position, what makes a bad Go position. They just use machine learning. So machine learning means like there's various mechanisms of doing it, but essentially what you're saying is I'll generate or I'll get and right now they actually generate those. In the past, the first version of AlphaGo just had a database of games, and then they had positions that led to a win by black. They had positions that led to a win by white, and they just tried to make a function that does a good job of predicting whether black or white would win using machine learning, meaning not by explicitly enumerating the rules about what makes a good position, but by just trying kind of every possible function from a big class of functions and seeing which ones predicts the best. So trying to do something that's a little bit like maybe what human Go players do, try to get an intuition for what makes for a good position. So that's maybe covered in third year. So in the future, it's a little bit complicated. So okay. So search again is just the enumeration of the possible ways in which the game can develop, and you're looking to make sure that you find a way to make your evaluation go up. So okay, so what we're doing in project 2 is Gomoku. So the terminology here, because it's played on a Go-like board, the pieces are called stones and they're black and white rather than being crosses and knots. Same principle. You need to get 5 pieces in a row, 5 stones in a row. So what would be a good evaluation function for Gomoku? So you want to get 5 in a row eventually, and you look at the board and you see stones. So this should give you an idea about what to look for, as well as our discussion of tic-tac-toe. So what do you, like anyone who plays Gomoku, what do you want, like short of just 5 in a row? What's a good thing to have? Yeah.
4 in a row and
yeah.
Space on both sides.
Exactly. Yeah. So 4 in a row with space on both sides. Unless your opponent is about to win, you won because it cannot be blocked from both sides. Let me type it out. So if you have a situation that's like this, and there's like white here and whatever, like black somewhere here, doesn't matter, then like all the whites are scattered, whatever, then there is really nothing the white can do, because white can block from this side, but then black just completes here or the other way, right? So another thing that you can do, so this is called an open sequence of 4 stones. So another thing that you can do is kind of the same idea, just with 2 of 3, right? So the idea here is if you have 2 sequences of 3 that are open, again, white can try to block this one, but then you make an open sequence of 4 over here, and white again is done. Right? So the basic idea here would be count up the number of open and semi-open sequences. So semi-open just means blocked from one side. So you can also add 2 if you want, right? And then if you have an open sequence of 4, you pretty much are winning. If you have 2 open sequences of 3, you're pretty much winning, and so on. So having a semi-open sequence of 3 might be useful, although it's probably not that useful. So from that, you can try. We need eventually to compare moves. So like which move is good, which move is not good. So we need a score, not just how many sequences of which lengths there are. So I made one for you. So this is this is the score function. So that's given to you, and that's already pre-computed. And here what we have is basically a function like this, right? So this uses a construct that I'll cover tomorrow, actually, but you don't need to understand the internals other than to just like look at the formula and say, okay, what we're doing here is we're saying count up how many open sequences for white there are and how many semi-open sequences from white there are of length 4. And if there are any, then black is doing really poorly, so we'll multiply the number of open sequences of white by minus 10,000. And that's because we're assuming that that white is about to make a move. So if white has any sequences of 4 that are open or semi-open, black is done. All right. And then if that doesn't enter it, if it does, then it's going to be extremely negative. Then we reward an open sequence of 4 for black with 500, a coefficient of 500, and then we give 50 for semi-open, because a semi-open of length 4 is really not that useful. It's just going to get blocked, right? And then if there is an open sequence of length 3, then we subtract, and so for white, then we subtract, and so on. So that's an example of an evaluation function that in practice works well. All right. Okay. Is there stuff on Discord? Okay. Thank you. So okay. Okay. So that's the function. Your job essentially is to just compute the number of open and semi-open sequences of black and white stones. So this is already made for you. What you need to do is write the function detect rows, and detect rows takes a board, it takes the color of the stone, and it takes the length of the sequence, and it should return the number of open and semi-open sequences of that color of that length. So that's one component of project 2. The other component of project 2 is the function that they call search max. Search max actually finds the move that maximizes the score for black. Okay, so the way you maximize the score for you find the move that maximizes the score for black is the same thing that you did in tic-tac-toe last week. You try every possible move, you record how much that got you. If that works, then great. If not, you undo and try again. Okay, so that's literally the same, or like almost the same thing as what you did in order to win in tic-tac-toe. So that's the assignment. It's basically detect rows. I provide some structure to you, some of which is mandatory, some of which is not mandatory. So the details are in the handout. Whatever functions I say are required are required. Anything else you can write or not write, it's up to you. I do force you into a certain structure that's not the most efficient, but I think the most straightforward. So if you, especially if you're stuck, if you say, I don't know how to do detect rows, try to follow step by step and do the functions that are listed in the handout first. That can help. At the same time, if you think that the way that I propose doing detect rows is kind of silly, you're not wrong. I just think it's like the easiest way to scaffold things. Okay. So this is that. And this is just the summary of how you would do the evaluation function. And this is how you would do search. So one thing to note is that the way we do search is a little bit silly. the only thing that we do is we look one move ahead, right? So that suggests that if, for example, you have a situation like this, that would count as that would count as, you know, a possibly semi-open sequence of 3, which is not that great. And the reason it doesn't seem that great is that in order to know that this is actually great, you need to say, well, like if I look one move ahead, I could have put a black stone here, and then I would have gotten a sequence of 5. So this you might say, well, like you should just account for that. It's just that the handout didn't. So just account for this kind of configuration in addition to an open sequence of 4, right? But you can also imagine those kind of deals where you have this thing, where this is really great. But again, in order to know that this is really great, you need to know that if you put one black stone there, then you'll have 2 open sequences of 3. So again, this is the kind of structure that implies that looking ahead by more than one move would be useful. It's just that it's expensive and difficult at this stage in the semester. So about like the lecture before last during this class, hopefully if we have time, I'll do look ahead by more than one move. It requires kind of advanced techniques, and really you need to wait until 190 in order to kind of fully handle those kind of situations. All right. So all the details about what to do are in the handout, but I'm happy to take questions about either what to do or the general philosophy, or we can move on. Okay, so let me just briefly, because the midterm is coming up soon. So the midterm is, you know, the Monday after reading week, right? The material is all the material through the lecture before reading week, as one might imagine. You can look at the old midterms, like I said. So there are solutions, there's marking schemes. People often ask, you know, how is it marked? Well, there's marking schemes for old midterms. You can just look it up. So in terms of what to expect, so similar format to old midterms, kind of similar to what we had done on Friday. So I think the Friday one, like I said, like I asked Samantha to say, was like slightly unrepresentative in that we just put one difficult question there. And then we also put maybe more questions than you would expect per minute, just because I didn't want to make it too short. So that was kind of a compromise in terms of how to fit something into 40 minutes. So looking at old midterms will give you a better idea of, you know, the general difficulty of what to expect. I also hope that just getting the practice this Friday gave you an idea of where you are. Tomorrow in the lab, is the lab tomorrow? No, the lab is on Thursday. So on Thursday in the lab, we'll also have some instructions about how to self-grade. So one issue I think that people often have is they kind of write the thing down and, you know, maybe you type it all in and it's exactly correct, and then you do know that it's exactly correct. But if it's not exactly correct, it can be challenging to know how far away you are from the solution. So we'll try to give you guidance about how to sort of self-grade as you prepare for the midterm. The short version of it is type it in, see if it runs, run some test cases, see if it works. It's highly unlikely that anything that's like more than 5 lines is going, not highly, but it's unlikely that anything that's like more than 5-10 lines is going to work if you just type it in verbatim. There's always typos, right? And that's fine. What you want to see is, did I hit kind of all the components? Did I put all the components together correctly? The way to know, the short version is try to fix the code that you actually wrote on paper so that it does actually work. And then ask, okay, what did I need to do in order to get from what I wrote to something that actually works? The difference between what you wrote and what is required in order to make it work. It's kind of what you've missed. It could be just small typos that nobody cares about. It could be something more important. So, okay. In terms of the composition, so I put some relatively easy problems, so the kind of thing that you would get in the beginning of the lab. And then I try to put in some problems that are solvable using approaches that is similar to what is needed for lab examples or lecture examples, or like we'll have like one online exercise that's very short. So sometimes, and what I mean by this is, like you've all been to high school, so you kind of know the idea of, you have a word problem and then you change up, apples to oranges, and then you have a different word problems. So that would be an example of something that's very close to an example that you've seen. In general, I try to say, okay, here is the kind of idea that you would need in order to solve this problem. So for example, if the problem is compute the sum of a list, well, what's the idea? Set up an accumulator variable. So accumulator is just what people call it, but it stores the running sum. And then, add each element in turn. Okay, so that would be the kind of example that we saw a million times in lecture and that you did in the lab as well. And then I would say, okay, what's a problem that's kind of similar in spirit, but not quite the same, right? So maybe I would say concatenate all the strings in L to one single string. And you can do it with literally the same code, except you need to change the S to be the empty string initially, and then you just keep adding up the strings, right? Yes.
Would you allow solutions like empty string dot join out? Or do you want to select active?
So yeah, so the question was like here, this is not the only possible solution. You could also do something that we hadn't done, but you can do what you were saying, like, is this allowed? The answer is look at the front page about what's allowed and what's not allowed. In general, what the front page says is just that anything that's valid Python is allowed, but you're not allowed to import anything that's not math. So any kind of valid Python code by default is allowed. Sometimes specific things would be banned per question. I would not say, except you cannot do this. That would not make sense. So I would never say like a particular thing is not allowed. I might ban importing. I might ban in the future, although not in the midterm. On the exams, you'll see examples where I'm saying you're not allowed helper functions. Right now, that doesn't make sense, but it will make, or if you know about recursion, it could make sense. So yeah, so stuff like that. All right. So okay. So that's kind of an example of the same kind of thing in spirit, but different because here you're dealing with strings or whatever. Or I could combine two ideas that you've seen that would be more difficult. So like concatenate all the digits in L stored as integers. And then, so the idea would be like L is like 1, 2, 9, 0, 8, whatever. And then in order to concatenate the digits, you need to first convert them into strings, and then you concatenate, right? So you would do something like this. So this is kind of going from an example that was definitely in lecture to an example that I don't know if we've done it in lecture or not, but that's kind of similar to maybe doing something that's combining several ideas from lecture. there's gonna be a range. Some are guaranteed to be very similar to the lab and the lecture. So I pay attention to that, and I intentionally put this kind of thing in. I also try to come up with something original. So sometimes, not every year, but often I would have a problem that's worth 10, 15% that I kind of call the A+ problem, where, like, in order to get 100, you need to solve like one difficult problem is the idea. And you'll see those as the last question on the midterm. Again, how does anyone compose those? I'm not saying everyone, but like almost everyone. So something like this. So like either I'm thinking this is something that we've seen in the lecture in the lab, so they should know this. And sometimes people get kind of, persnickety about this. Or kind of the second bullet point is the problematic one, where this looks straightforward to me, so I'll just put it on the midterm for easy marks. And sometimes it turns out straightforward, sometimes maybe not so much. And then this is something that I know is a hard problem, and this is specifically to distinguish like who should get an A+ and who should get an A in this course. So sometimes I can fit a problem like that in the midterm, sometimes not. Like you compose a midterm and then you say, oh, it's too long, I got to take something out. And sometimes what gets taken out is the hard problem. So, there's surprises. You'll see there's like, I think they're all mostly similar from year to year, but there's some variation. So in general, like you've done a couple tests already, so I think you probably know how it goes. So just, do what you normally did in high school. If you learn any lessons from the midterms that you wrote so far, then so much the better. I would say one thing that I would suggest that's maybe not obvious is if you look at the problem and it looks difficult, like how would they solve it? Probably there is a way to connect it to something from the lab and the lecture, right? So even if it's not obvious, like, there's like an infinity of very difficult problems that no one has a way to solve, and there's no point of putting them on the exam. So if it's in the exam, there's probably a solution. I think knowing that there's probably a solution and that probably it connects to something from lecture and lab should help, because it helps you eliminate possible approaches. With that said, sometimes I try to come up with something original as well. So again, if you're stuck, just ask this, like, what can I do to make progress? That sometimes gets you part marks if you get something that's approximately right. And it also can help you get full marks, because once you get an idea of how to make progress, then you say, okay, like, how do I go further from there? So at this point, I tell you the Carnegie Hall joke. Carnegie Hall is a famous music venue in New York City. Jascha Heifetz is a famous violinist, and the joke goes that there's a tourist who goes around New York City lost, finds the famous violinist Jascha Heifetz, and says, "Sir, excuse me, how do I get to Carnegie Hall?" To which famous violinist Jascha Heifetz replies, "Practice, my young man, practice." So do that. That's really the only way to learn. So, do the old midterms. All right. Okay. All right. So we have some time to go back to the handout. We did problem one, and can someone give me one of the handouts? Is there extras? All right, thank you. So we kind of had the long version of the rules. I want to do a short version of the rules of how to process those things. So we basically have we basically have those rules. So if we have A equals B, then there's two situations. B is a new object. You place B in memory. And then copy the address of B in the variable table to A. Right? So that's always the process. So if B is a new object, you need to first place it in memory. Either way, once you have the address of B, you go to the variable table, you copy that to A, always. So that's the rule. So when calling a function, so calling a function is something like this. And that's the same as A equals B, but A is in the local variable table. And then the third thing that we need, to pay attention to is nested lists need to be unrolled. So if you follow those, you can basically do everything. So let me do B, and then how many people have done C already on their own? Okay, not many. That's okay. So let me do B, and then we'll get started on C, and then we'll do C tomorrow. So B is like this. And I know we did it already, but it was a while. So I'm going to my memory table thing. I'm copying it. Okay, you know what? I'm not going to copy it so that you'll have it as well. So this looks like this. So what I'll do again, so I'll just place 5, 6, 7 into memory. And now, so here, technically, F is a variable, whatever. I'm not going to bother with that. So, and on the exam, you don't have to do the tables. You just have to do prediction. So here we're saying L is 6, 7. So the rule says new object, place it in memory. So new object, place it in memory means place it here. So this is going to be 10, 10, 10, 20. Like so. And now that it's in memory, L is 1030. The autocomplete gets better and better as a feature, so that's good. Okay. Yeah. Why does so you mean like those guys?
Yeah. Those guys go up by 10, but
Yeah. Oh, I see. So those, sorry. So the question is like, why do those go up by 10 and the ones on the handout go up by 40? That's a fair question. I'll make both of them go up by 40. The real answer is they don't go up by either 10 or 40. This is just a convenient way for me to write with kind of division so that they're all kind of look divisible by 10. Really, if anything, they go up by 32, but it's more complicated than that because if they're, so here I'm storing two things. Obviously, I cannot store, 200 things in between 1120 and 1160. There's just not space. So I'm just pretending that it's fine. But yeah, thank you. So I fixed it. So now it goes up by 40, except, okay, I'm not going to fix it because then I have to fix the other things. So I'll do it like this. Sorry. So, okay. So that's 1010, 1020. So now I'm saying f of L. So the rule here is it's as if I'm saying local L is equal to global L. And that means you copy the address from here to here. So that is rule number 2. Okay. I can copy, I can screenshot the rules. Well, I can maybe screenshot the rules. Okay, that will make them a little bit easier to look up. Okay, so it is already shared. I can see because someone's looking at it. So, so this is the thing from the slides. So, okay. So now we're saying L at 1 equals 6. So 6 is not a new object. Okay, I can see that people found it. So 6 is not a new object. Don't need to place it in memory. What we need is we need to copy the address to which 6 corresponds to L at 1. So L is 1030, L at 1 is here. So we're copying this to here. So this becomes 1010. Here, new object on the right. So we got to place it in memory first. And then we got to copy the address. So place 56 in memory. So this would be 1000, 1010. Address over here. So this becomes 1040. We then print L. So here we print L, the global L. So we print the 1030. So the 1030 at this point is 66. Sorry, yeah, 66. Oh, actually we said L at 1, yeah, 66. Okay. So every time just think, okay, like which of the 3 rules applies, that basically should do it. So the only subtlety is what happens with nested lists. So technically the rules apply, but it's slightly difficult. So basically it's like this. If you're saying L, so this is exercise C. So we're just starting it. So if you're saying L is something like this, and then you're saying L1 is something like this, then the new object is the outer list, but L at 0 is just an address. Okay, so what's going to happen here is you're going to create 5, 6 in memory. Then you're going to create this list in memory. And then this is going to be a new list, but L at 0 is still this old list. So you're going to copy the address of this to here. All right. Okay, so think about exercise C, and we'll come back to it tomorrow. All right, see ya. Bye.